So here we are at chapter 6, and I'm going to try to do this like we are in class. I would tell you that there are 3 sections we're going to cover: normal distributions, applications of the normal distribution, and then a thing called the central limit theorem. This is what I look at when we're in class, so now you're watching my book. Keep out your book, underline, highlight. Cool thing is you can stop the recording and then underline and then start the recording back up again. Just as in class, I'm not going to be able to read everything, but it's all here for you to read later. I want to point out on this one that we're going to talk about a normal distribution. In class, I would get all of you to read, but as it is now, it's just me. So I'll get to read to you. And the parts I want to read are right here, and you can see where they're underlined. And so you've got your ebook open, or you've got your regular book open. And then I'll read here. Finally, if it were possible to measure exactly the heights of all adult females in the United States and plot them, the histogram would approach what is called a normal distribution curve, as shown above. The distribution is also known as a bell curve, or a Gaussian distribution curve, named for the German mathematician Carl Friedrich Gauss. He derived this equation. No variable fits a normal distribution perfectly. Since a normal distribution is a theoretical one, however, a normal distribution can be used to describe many variables because the deviations from a normal are very small. And this concept can be explained later. But this chapter is also going to present the properties of a normal distribution and discuss its applications. Then a very important fact about normal distribution called central limit theorem will be explained. Go on over to page 305. On 305, you see a green box. Highlighting, underlining the green box. If a random variable has a probability distribution whose graph is, start really underlining, continuous, bell-shaped, and symmetric, then we're going to call it a normal distribution. The graph is called a normal distribution curve. Go on with me to page 306. On 306, I would have us read all of this in class. And we actually got to do this before the spring break. Pointing out the same parts again. Number 1, a normal distribution is bell-shaped. So it's a summary of the properties. The mean, median, and mode are located at the center. I'm going to scoot on over to page 307, and here's a picture. The mean, median, and mode all line up in the center. Step 3, or thought 3, is called unimodal. It is symmetric. It's the same on both sides, and the curve is continuous, no gaps. The curve never touches the x-axis, and we talked about asymptotic in class, that on both sides it will never touch going to the left or to the right. The total area, highlight, underline, scribble, under this curve is equal to either what we would call 1 or 100%. And it may seem unusual. We could prove it in calculus. We're not going to right now. Then here come some pretty important numbers. So down at the bottom, well, before I get there, the empirical rule for data, symmetric, a little bit more stuff going on here. Left and right, we'll talk about that at the top of the next page. So what I need you to see are these numbers, and I need you to memorize these 3 in the middle. When we are 1 standard deviation on each side of center of the median and the mean and the mode, in this case the mean, you have about 68% of the data values. If we go on out 2 standard deviations, negative direction, positive direction, we get about 95% of the data. And then 3 standard deviations, about 99.7. These are the 3 numbers I want you to memorize, and the corresponding deviations. Up here I wrote us some notes looking at corresponding probability, and so this was an example I would use in class. If we drew this normal curve and we put the mean at 100 and a standard deviation of 15. What is the range of variables that defines the area corresponding to the probability of approximately 95%? So coming back down here, about 95% would be the same as 2 standard deviations on both sides of the mean. And so if I go back up here in my sample problem, if I go 2 standard deviations and 2 standard deviations, if we're talking that the standard deviation is 15, then we would go up 15, up another 15, and that would get us to 2 standard deviations above. And then we would go down 15 and down 15 more. And so the range of the variable is defined at the area under the curve, that is 95%, approximately 95% of the data values, is going to be from 70 to 130. I'd like to point out some interesting facts about these 3 curves. This is a normal curve, and we saw that the mean, median, and mode stack. They are all the same theoretically. But here's our left-tailed skew, and here's our right-tailed skew. And when we were in class, I did point out find mode. Mode is going to be the one with the most. Mode is going to be the one in the most. So notice how mode is on the right for the left-tailed skew, and it's on the left for the right-tailed skew, or however you want to see it or say it. Median is always in the middle. So once you can figure out median's in the middle and mode is the highest one, well, mean goes on the other spot, on the other side of median from the mode. Mean is the average. I also want to point out standard. When we're looking at standard, it's a normal distribution with a mean of 0 and a standard deviation of 1. And if you look down at the bottom, you see our mean is at 0. We have plus 1, minus 1, minus 2, plus 2, and plus 3, minus 3. And then in class, we took time to look at how are they getting these numbers. Remember that 1 standard deviation in either direction on the other page we looked at is about 68%. And if we take that 68, which covers this whole area, and cut it in half, that gets us about 34 and 34. These numbers are more accurate. These are good about numbers. And if we continue that process, we're going to get about numbers throughout the rest of the standard or a normal distribution. And I bet y'all can hear my dogs. And so looking here where it says all normally distributed variables, another thing I'd like you to highlight or underline, which is on page 308, is that all normally distributed variables can be transformed into the, the standard. The standard was on the other page where 0 is our mean, and then we use 1, 2, 3 to go out on the standard deviations. This should look very familiar. And in fact, someone in class said, didn't we already do this? Yes. We've already played around with it, and I want to continue to read a little bit more about this. Once the x values are transformed by using this formula, the data value minus the mean divided by the standard deviation, they're called z-values or z-scores. And they're actually the number of standard deviations how far it is from the mean. If it's plus, we're going to be going to the right, and if it's a minus, we're going to be going to the left. And it gives an area to 4 decimal places under the standard normal curve. To find this, it tells us to, step 1, draw a normal distribution. On your tests, I will be looking for first a drawing and a shade. I'm not looking for beautiful drawings, but I believe the drawing is what starts you on the right path to solving for all the rest of the stuff that we're going to be doing. And then step 2, we're going to find an approximate figure in a procedure table. So make sure that for what we're doing, you have out your formula card, you have out your calculator, and that you have found from the video I just sent earlier today, the need help tile. It's not a tile, but it's a file in D2L. Lots of stuff lots of places to get help, but we're going to continue and look at how do we calculate right here, finding area under this normal curve. That's what we're going to be looking for. So the thing I like to write on this one, anytime we're looking for the area to the left of this z-score, to the left of the z-score, anytime we're looking for that, then when we go look at this chart, it is what it is. I can remember that because if I look down here, it's the same kind of concept that we're looking at the area to the left of the z-score. But we're also going to find areas to the right, and we're going to find areas in between two of the z-scores. Before we go on and look at these examples, I want us to practice. They're asking us to find a value for the area, right here, the area value for z equals 1.39. So I'm going to look on my chart, and I'm going to notice that all of these are positives. And this is table E. And then I'm going to look at table E on the back side and notice that all of these are negative. Since they're asking us to find a positive 1.39, I'm going to go to this side of the chart, which is positive. Sorry about the glare. It feels just like in classroom. And when I look here, I've got the 1.3, but it was 1.39. So now I'm going to go at my 1.3. I'm going to go all the way across, and notice at the top we have the hundredths value. So I need to go to the 9. So when I run my finger all the way across from 1.3 all the way over to 1.39, I get a value of the area under the curve of 0.9177. And that's what they came up with. And a little bit more description, maybe? Nope. And so what that is telling me is if I am looking at and it is what it is, then I would be able to say that 91.8%, 91.77% of the values under this curve with a z-score of 1.39, those values represent 91.77% of the values. So now what's going to happen is this video is over, and I'm going to show you in D2L a video to go look at and then come back and do this problem. A video to look at and then come back and do this problem. And we'll repeat that process until, and this is a sad little note here, this is where we were going to start when we got back from spring break. But we have started, and it just looks a little differently, and I'm learning information, and so are you guys. So hang in there. That's all I'm going to show you in this video for section 6.1. And now it's your turn to go watch additional videos, work the additional examples, and then go do the homework and connect math for 6.1.